In this lesson, we will be looking at the independence of irrelevant alternatives, or IIA criterion, and demonstrating how the method of pairwise comparison violates this fairness criterion. Simply stated, IIA says that if a voting method is to be fair, voters' preference for some candidate X over some candidate Y should not depend in any way on a third candidate Z. In particular, if X would win the election when Z is not a candidate, then Y should not become the winner when Z joins the race. While this is fairly obvious for an individual voter, it is often not the case when we consider groups of voters. All of these voting methods we have studied can violate the independence of irrelevant alternatives. Let's focus on the method of pairwise comparisons, or Copeland's method. Recall that Copeland's method asks us to examine every possible head-to-head pairing between the candidates. Each matchup is worth 1 point. In the event of a tie, the candidates split the point. The overall winner is the candidate with the most points when all the matchups are tallied. In order to construct an example of how this method violates IIA, we will need an election with several candidates. We will start with 4 candidates, which lead to 6 pairwise matchups. If we remove one of the candidates, say Davis, the number of pairings drops to 3. For our example, let's have Anderson win when all 4 candidates are in the race, but have Baker as the winner when Davis leaves the race. If we can do this, we would show that pairwise comparison violates the independence of irrelevant alternatives. To accomplish our task, we need Anderson to lose points when Davis drops out. This would happen if Anderson beats Davis in their head-to-head pairing. On the left, Anderson gets a point for beating Davis, but on the right, that point no longer counts because Davis is no longer running. Next, if Baker is going to become the winner when Davis drops out, we need Baker to not lose any points when Davis leaves. The only way to accomplish this is to have Baker lose to Davis head-to-head. Then he would never receive that point to begin with. However, if Baker is going to be the new winner, he needs some points, so we'll have Baker defeat Cooper one-on-one. This is where it gets tricky. Currently, on the left, Anderson, Baker, and Davis are all tied with 1 point apiece, while on the right, Baker is the only remaining candidate with a point. If Anderson defeats Baker one-on-one, then Baker will not win on the right. On the other hand, if Baker defeats Anderson one-on-one, then Anderson will not win on the left. Therefore, they must tie. At this point, on the left, with all the 4 candidates in the race, Anderson and Baker are tied at 1.5 points each, while on the right, Baker leads by 1 point. So in the matchup between Anderson and Cooper, we need Anderson to get half a point. That will be enough to break his tie with Baker on the left, but not enough to catch Baker on the right. In other words, we need Anderson and Cooper to tie as well. The only remaining pairing is the one between Cooper and Davis. Anderson already has 2 points on the left, while Cooper has only 1/2. Cooper cannot catch Anderson. Davis, however, has 1 point. If Davis were to win this matchup, he would be tied with Anderson. The simplest thing is to give Cooper the win over Davis. As it stands, with all 4 candidates in the race, Anderson has 2 points, Baker and Cooper each have 1.5, and Davis, our irrelevant alternative, has only 1. Thus, Anderson would be declared the winner. However, if Davis were to drop out of the race, the situation would change. Anderson and Cooper would each lose a point, while Baker would retain all of his. With 1.5 points, Baker would be declared the winner. This is exactly what we want if such an outcome is possible. We now have to construct a voter preference schedule that actually leads to this outcome to show it can happen. With 4 candidates, there are actually 24 distinct rankings possible, but we'll try to use only a few. Here, I've started the preference table by putting 5 voters in each of the first 4 columns. There's nothing special about having 5 voters, but this will make it relatively easy to obtain the ties we are looking for, and if we have to tweak the numbers to make things work, I have room to raise or lower the vote counts as needed. We want A to beat or tie every other candidate, and D to come in last. So I filled in the first column with the candidates in order A, B, C, D. Since B is going to be our winner when D drops out of the race, we need to give B some votes as well. By ranking the candidates in the order B, C, A, D, we have ranked B above C in both columns, so B is currently winning that matchup as desired. 5 voters have A above B, while the other 5 have B over A, so A and B are tied. Similarly, we see that A and C are currently tied. All the voters so far prefer C over D. So far, so good. The only one-on-one matchup that is not working yet is B versus D. We need Davis to beat Baker, but so far we have all 10 voters ranking D last. As we fill in the next two columns, we'll make sure to rank Davis above Baker. If we give C the top spot in the next column, then C will be ranked above D in all three columns, giving him the win over D regardless of how we fill in the fourth set of rankings. If A is also ranked above D, then A will also be guaranteed the win in his head-to-head matchup with D. So we will place A second in this column. Ranking D above B as promised gives the orderings for the third column as C, A, D, B. For the fourth column, we again want D ranked above B. We also need to restore the ties that we broke when assigning the rankings in the third column. Since the third has A above B, in the fourth we need B above A to restore the tie. Likewise, since C is ranked above A in the third, in the fourth we will rank A above C. This gives the ordering for the fourth column as D, B, A, C. At this point, A is tied with B, A is also tied with C, and A defeats D head-to-head. All the pairings involving A are exactly how we want them. B is preferred head-to-head over C, and C is preferred over D. Thus, all the matchups involving C are how we want them. However, as our table stands right now, B and D are tied with 10 votes apiece. We need B to lose this matchup so that when Davis is removed, B's points are unaffected. We could try to work with just these four columns, changing the vote counts up or down, but it might be difficult to change the results for Baker versus Davis without affecting the other matchups, particularly those involving the ties. Instead, we have chosen to add a couple voters in each of the remaining columns in the table. We can guarantee the outcomes between A, B, and C remain unchanged if we make sure that in each pairing both candidates receive the same number of votes. For example, in the second to last column I ranked A above C, so in the last column I make sure that C is above A. That way each receives 2 new votes and the candidates remain tied in their head-to-head comparison. Note that one of the new columns has A over B, while the other ranks B over A, one ranks C over B, and the other B over C. We have left the fourth choice open right now, but in order to break the tie between Baker and Davis, we'll need D ranked above B in both columns. To accomplish this, we shift Baker and any candidates ranked below him down to open up a slot for Davis. Notice that the relative positions of A, B, and C have not changed. When we insert D in the open spaces, 2 things happen. First, D receives 4 more votes in his 1-to-1 pairing against B, making D the winner of that matchup. Second, we can see that the voters in the second to last column rank A over C and C over D, whereas in the last column, the voters rank D over C and C over A. This situation is completely analogous to what we saw in the previous slide, guaranteeing that the outcomes of pairings involving these 3 candidates remain unchanged. Let's check the results. Here we have the completed voter preference schedule on the left. On the right, we have the resulting vote tallies for each pairwise matchup in this example. We see that in both A versus B and A versus C, the candidates are tied at 12 votes apiece. A defeats D, B defeats C, and C defeats D by a count of 17-7 in each case. Finally, by a score of 14-10, D defeats B. Summarizing the results, on the left with all 4 candidates and on the right with Davis removed, we see we have achieved our goal. In the example we constructed, Anderson would be declared the winner when these 4 choices are offered, but using the method of pairwise comparisons, the voters would select Baker instead if Davis were not in the offering. This example clearly demonstrates that the method of pairwise comparisons does not always satisfy the independence of irrelevant alternatives criterion.